All right, let's dive into this explainer on the ultimate, old-school mathematical lie detector used to test today's absolute most cutting-edge AI. You know, when we look at modern deep learning, we see these massive frameworks calculating exact derivatives at lightning speed. But underneath all that shiny surface, engineers actually rely on a surprisingly simple foundational technique. It's called numerical gradient approximation, and honestly, it's pretty much the only way to ensure the whole system isn't just silently collapsing.
We've got a lot of fascinating ground to cover today. 1. AI's ultimate lie detector. 2. The mountain climber intuition. 3. The magic of centering. 4. Real-world AI applications. And 5. Common engineering traps. Let's get right into it.
Section 1. AI's ultimate lie detector. Finding bugs in AI.
So, this all starts with a pretty terrifying reality of modern deep learning. We all know modern AI is built on automatic differentiation, or Autograd. And look, Autograd is an absolute engineering marvel. It computes exact derivatives. But it has a fatal vulnerability. It entirely relies on the manual code written for the backward pass. So imagine you invent a cool new neural network layer, maybe a novel activation function, or a custom low-level GPU kernel. If you make a single typo in that backward pass, Autograd has no idea. It will happily and silently compute a mathematically perfect, yet completely wrong gradient. Your model trains on this incorrect data and you're left with mysterious failures that could literally take you weeks to debug.
Think of Autograd as an architect's blueprint. It's incredibly fast, it gives you an exact plan to build a skyscraper, but it's highly vulnerable to human error. Numerical gradient approximation, on the other hand, is like the surveyor's transit level. It doesn't care about the complex software or the calculus rules at all. It just checks the physical ground truth by querying the function directly. It's slow, it's tedious, but it is absolutely infallible.
Section 2. The mountain climber intuition. Visualizing the math.
To really get how this surveyor works, let's strip away the code for a second. Imagine you're blindfolded on the side of a mountain, and you want to know the exact slope of the ground directly under your foot. You obviously don't know the mathematical equation of the mountain. All you have is a measuring stick and an altimeter. So here's what you do. You take one tiny step forward, let's call that plus h, and measure your altitude. Then you step back to the middle, take one tiny step backward, minus h, and measure your altitude again. Subtract the backward altitude from the forward, divide by the total distance you walked, which is 2h, and boom, there you have it. Because mountains are generally smooth, this simple average is an incredibly accurate proxy for the instantaneous slope right under your foot. You've just approximated a derivative using nothing but 2 altimeter readings and some basic arithmetic.
Section 3. The magic of centering. Canceling the errors.
Now you might be wondering, why go through the trouble of stepping both forward and backward? Why not just take one step forward and compare it to where you're currently standing? Well, think about the visual difference between those two approaches. A one-sided approach draws a line between your starting point and the forward point. Because curves, bend, this line gets skewed. It sits slightly above or below the true tangent line, so it suffers from a systematic error. But the centered approach, where we step forward and backward, draws a line that perfectly straddles the original point. The bending of the curve on the right beautifully cancels out the bending of the curve on the left. So you get a line that's almost perfectly parallel to the true tangent.
Let's peek at the mathematical engine running this. When we actually write out the math formulas, specifically the Taylor expansions, for our forward step and backward step, and then subtract them, something honestly miraculous happens. The baseline values cancel out, and crucially, the second derivative terms completely cancel out. That means our absolute biggest source of error just vanishes into thin air, leaving us with a much, much smaller second-order error.
So why does a second-order error actually matter in practice? Well, if you have a first-order error and you shrink your step size by a factor of 10, your accuracy gets 10 times better. Fair enough. But with the center difference leaving a second-order error, shrinking your step size by a factor of 10 makes your approximation an astonishing 100 times more accurate. It is an immense leap in precision. You're getting practically free accuracy for basically zero extra computational cost.
Section 4. Real-world AI applications. Where is this used? Okay, so you might be thinking, if this is so magically accurate, why on earth don't we just use it to train all our AI models? Well, because the computational cost is absolutely staggering. To check the gradients of a model with n parameters, you literally have to run a sequential for loop n times. If your model takes just 1 single second for a forward pass and has a relatively tiny 1 million parameters, checking the gradients numerically wouldn't take seconds. It would take 11.5 days. That completely destroys the parallel processing that our GPUs are built for.
So, okay, we don't train with it, but engineers still rely on it heavily for some very crucial specific tasks. First up, custom code. When developers wrote Flash Attention, which is a highly optimized custom CUDA kernel to speed up transformers, Autograd couldn't see inside their custom C+ code. They had to use numerical approximation to unit test their manual backward pass before deploying it. Second, reinforcement learning, where the environment simulator is often just a non-differentiable black box. And third, adversarial attacks, where hackers actually estimate gradients to fool models that use discrete, non-differentiable layers.
And this next part brilliantly illustrates how the research frontier is evolving. Storing the computation graph for backpropagation is incredibly memory-intensive. So researchers recently asked, can we use numerical proxies to bypass backpropagation entirely? Using a technique called zeroth-order LLM optimization, or MISO, they fine-tuned a massive 30 billion parameter language model without computing a single backward pass. By basically treating the model as a black box and perturbing weights using a variation of this numerical approximation, they dropped the memory cost from 120 gigabytes down to less than 1 gigabyte. That means fine-tuning a massive model suddenly becomes totally possible on a single standard GPU. How cool is that?
Section 5. Common engineering traps. Common pitfalls.
Deploying this surveyor's tool isn't foolproof, though. Let's wrap up with the traps you absolutely need to avoid. Imagine you've just written your custom neural network layer. You run your numerical gradient check to verify your math, and it just returns exactly 0.0 across the board, even though you know for a fact your analytical gradients are non-zero. So what went wrong?
There are three really likely culprits here. First is what I call the Goldilocks problem. If your step size, your h, is incredibly small, like 10 to the negative 20, the finite precision of float 32 rounding kicks in. Your forward and backward steps round to the exact same mathematical value inside the computer. So when you subtract them, you get a perfect 0. The standard engineering fix is to just use a step size of 10 to the negative 5. Second is a silent killer, forgetting to turn off dropout or batch norm. If you have randomness changing the network between your forward and backward steps, you're literally comparing apples to oranges, and the check will fail spectacularly. You always have to set the model to evaluation mode. Finally, beware the relative difference trap. If your true gradient is a massive number like 1 million, an absolute error of 0.5 is tiny. But if the true gradient is 0.0001, that exact same 0.5 error is catastrophic. Always normalize the error relative to the size of the gradients.
So the crucial point to take away is our mental model. Do not try to train a network with numerical gradients. Instead, use numerical approximation as the surveyor's transit level. You use it once, slowly and methodically, just to verify that the architect's fast, exact Autograd blueprint matches reality. And once it's verified, you confidently build the skyscraper with the blueprint.
But looking to the future, this leaves us with a pretty fascinating dilemma. As AI models continue scaling toward trillions of parameters, the memory overhead required to just store the autograph computation graph is becoming an insurmountable wall. With breakthroughs like MISO successfully fine-tuning massive models without any backpropagation, we really have to ask, as we reach the absolute limits of exact calculus in software, will the slow, steady surveyor eventually replace the blueprint entirely? It's a fundamental question about the future of AI optimization, and honestly, it might just reshape how we build the next generation of models entirely.